Hey everybody, it's Mr. Carr again. Today we're going to look at 7.5 day 2. Our focus here is just on projectile motion. So the idea about projectile motion is it's any object that is kind of launched in the air follows this parameter or parabola kind of path, parabola path, a parabolic path, I should say. Okay. So now the idea here is that depending on how we launch on the angle, we can model both the horizontal and the vertical distance, or the horizontal distance and the vertical position based on these two, basically these parametric curve, or we can model it as a parametric curve. In the x direction, it is going to equal to t times the initial velocity times the cosine of theta. In the y direction, it's t times the initial velocity times sine theta minus 16t squared plus h of 0, which is our initial height. Okay, so g is going to be our gravitational constant. So we look at this one here, it's 1/2 of g times t squared. But we're gonna, in terms of if we're dealing with feet, then we're going to deal with g equals 32 feet per square because that's basically what we're working with there. So that's why this turns into a negative 16 here. Now, a lot of the problems we'll work with are going to be dealing with feet, but things change a little bit if you are dealing with meters is the idea. Okay, so from here, let's take a look at one of our examples. Shane Leckler of the Oakland Raiders has a record career punting average with an average of 46.47 yards. Suppose that he kicked the ball with an initial velocity of 26 yards per second and an angle of 72 degrees. Okay. How far will the ball travel horizontally if he punts it with an initial height of 1 yard? What was the maximum height? So we're going to look at this. So the first thing I want to do is let's figure out what we have. We have an initial velocity here. We have an initial height. And we have our theta that's given like that. Okay. But the other thing we have to be aware of is that everything is in terms of yards. If we're going to use these, like g equals 32 feet per second, and we're going to use this formula, then we need to turn everything into feet. So start with that. I'm going to say my initial velocity is going to be, instead of 26 yards per second, we're going to multiply that by 3 feet in 1 yard so that we can have an initial velocity of, it'll be 78 feet per second. Okay, so that means I have that for my initial velocity. My initial height is 1 yard, so that's going to be 3 feet when we work through this. Okay, so in this scenario, we're going to look at, let's see here, how far the ball travel horizontally if he punts it with an initial height of 1 yard. So the idea is that we need to find from this the amount of time it takes for it to get up to a certain height, back down to 0. So in that case, I'm going to say when the vertical height is 0, so that's going to equal to t times v times sine of theta. So that's going to be t times initial v, which is 78, times the sine of 72, minus 16t squared, plus my initial height of 3. Okay, so from this scenario here, I can kind of rearrange it a little bit. So if I look at this as, we can multiply this through here. So I'll just leave it as 78 times the sine of 72 times t minus 16t squared plus 3. Then I'm going to use this as a, this is going to be my b, and this will be my c. So we're just going to go through and do my quadratic formula now. So when I do that, it's going to be a little bit complicated because the decimal number of 78 times sine of 72, but it just need to make sure you keep everything in track. So it will look something like this. It'll be negative b, so it'll be negative 78 times the sine of 72, plus or minus 78 times the sine of 72 squared, minus 4 times a times c, all over 2 times a. So when I do that, I'm going to come out and calculate a time of 4.68. You'll get 2 times, but just do the positive one because the negative one's not going to help us. Okay, so we got the 4.68 is the amount of time it takes for the ball to travel up and then back down. So now that's going to go into, separate this too, into my horizontal distance one. We have t and the initial velocity and our cosine theta. So the x distance it travels is going to equal to 4.68 multiplied by my initial velocity, so 78 feet per second, times the cosine of 72 here. Okay, so we multiply all those out, we get 112.80 feet. Or if you want to divide it by 3, it's going to travel 37.60 yards. Okay, we'll do part 2 there, the maximum height on my next slide here, because I'm running out of space. So we want to find the maximum height now of the ball. Okay, so in this case, what you're going to want to do is you're going to want to pull up the graph of this sorry, the graph of this in order to get that out. So when I graph this, all I really care about is the vertical position here. Okay, so I'm going to go off of that one of graphing that using kind of like this information here. So I'm going to graph it with, instead of t, I'll just make it as an x. So I'm going to go ahead and pull that up in Desmos in just a second here. Yeah, sorry, give me one right there. Okay, so here I put it into Desmos, or you can put in any graphing calculator that you want in this case. Just make sure that you're going to type it in like this, where it's 78 times the sine of 72x, okay, minus 16x squared plus 3. The other part of this is make sure that you are in degrees. So I want this to be degrees because I'm doing 72 degrees here, not radians. So when I do this, you can see the path. This is basically modeling the vertical path of the punt. It's going up in the air, it goes way up here to that point. So I just need to interpret this. Remember, x in my scenario that I put in Desmos here is time, and the whole function is the vertical position here. So after 2.32 seconds, okay, we're going to be at 88.99 or 88, yeah, 88.99. So if I come back here, we know that from the graph, whoops, from my graph here, it's going to do something like this, where it goes up in the air and it comes down. So up here is that maximum point. So it's happening at 2.32, comma 88.99. Okay. So if he kicked it with initial velocity, what was the maximum height of the ball? Is just this one right here. So from our graph, we know that the maximum height is 88.9, 99. Well, I did that in terms of, yeah, I did it in terms of feet. So 88.99 feet in this case. Okay, and that is it for today. So again, we're just looking at this one type of problem. The key about these projectile motion problems is that we have both a horizontal movement as well as a vertical movement. So everything is moving like when a thing moves on a curve like this, it has an X and a Y direction that it's moving is the idea. Okay, and that's it for today. Take care, everyone.